Whenever a phenol molecule is brought to the vicinity of a base, it automatically becomes acidic. Now, being acidic in this sense means that phenol is able to lose a proton to a base. So in this lesson, we are going to use structural equations only to show that phenol is acidic. So we start by drawing the structure of phenol. Now, in the presence of a base, this particular proton becomes susceptible to being lost. Oxygen is more electronegative than hydrogen. What this implies is that the bond pair of electrons are going to shift to oxygen. So the arrow goes from the bond to the oxygen atom that is more electronegative, creating a free hydrogen ion called proton, which is positively charged. This positive charge will now instigate OH minus from the base to donate a lone pair. Remember, OH minus has only one bond, so it has 3 lone pairs of electrons. So one of the lone pairs will move to the proton that is lost. OH plus H will now leave as water, creating an ion called phenoxide ion. Now, there are 2 lone pairs already, plus the bond pair that moved to oxygen, creating an additional lone pair. And that is what makes the oxygen part of this molecule negatively charged. What happens to the electron that is left behind? This electron cannot be localized at a point. It has to be delocalized inside the benzene ring in order to stabilize the whole structure. Okay, let me bring the negative charge this side. Then this lone pair will move to form a double bond between oxygen and benzene ring. Creating a double bond here makes this carbon to acquire 5 bonds instead of 4. And because of that, the bonded electrons, the pi electrons here, will move to this carbon. And this will create a carbanion, negatively charged carbon here. And because of that, the phenoxide ring will automatically enter resonance. And to yield the next resonance contributor, which is this double bond here now, lone pair, and we have negative charge here. This is a resonance contributor. Now, I don't want to continue this way because of space. Let me come down. Another resonance contributor is achieved when this particular lone pair moves to this place, thus, and this particular bond moves to this carbon, and we have this. This is another resonance contributor. Remember, the negative charge was here, and then it moved down here to form a double bond. And the formation of the double bond made this particular double bond to shift here in form of a negative charge to create another carbanion. It has not finished. This negative charge is capable of moving to this place to establish a double bond, so that this double bond will re-establish a carbanion here. And we have another contributor. The negative charge is now here, double bond here, double bond here. This particular negative charge is capable of moving to this place again to re-establish a double bond here. And this double bond going to the oxygen again. And immediately that happens, you go back to the first structure. And that is why this is called resonance or resonance stabilization as a result of electron delocalization. So these 4 structures, they are not real structures. They are the resonance intermediates, the effort of this particular phenoxide ion to stabilize itself as a result of deprotonation of phenol. And this resonance stabilization is the reason why phenol will even lose hydrogen ion and become acidic. If the phenoxide ion is not stabilized in this manner, it means that phenol will not be able to act as an acid. I hope you got value. If you did, click on like, comment, share the video, tag your friends, follow and subscribe to my YouTube channel.